Hello, everyone. Thanks for coming. In this talk, I will talk about the way to make Valkey multi-threaded, and then we utilize Userspace RCU for memory recommendation. So the idea is we want to recognize the problem about concurrency existing in current code base. And we try to improve the concurrency capability by means of integration of Userspace RCU. And then we want to modify the existing code base for better event-driven concurrency in the minimal effort. And then I want to introduce the code base for the research prototype named after Redis. So right now, you can check the source code on GitHub, which is multi-threaded Redis fork. So we introduced several changes. The first thing is master worker pattern. Second, we want to refine the existing event loop, making it work per thread I/O model. And then we want to utilize RCU for lock-free operation, meaning that we ensure only one writer along with multiple reader to achieve optimal read performance. After all, I will show you some number for the research prototype. In fact, I'm not going to submit the pull request for the Valkey since I need to talk about the developer in order to recognize the way how can we collaborate. And the code base was based on the code drop of my previous paper, so it takes time to replace and collaborate. And I think that's the reason why I stand here to invite more discussion here. So the challenge behind the concurrency issues can be classified as following. So the first thing is the bottleneck about the connection management. So the traditional Redis accept connection on a single thread, and this is the bottleneck for I/O. And then the use scenario of Valkey is quite different from the typical usage. So most operations are around the reading, and less than 10% is dedicated to write, meaning that we should introduce more efficient way to deal with such a symmetric operation. And it's quite challenging to introduce true concurrency model for existing Valkey code base, and we are trying to achieve this in meaningful effort. And the last thing is memory management. In the single thread model, it's quite straightforward to manage the object, but for multi-threading code base, it's totally different thing. Here, I'm going to evaluate several approach. So this is the traditional thread per connection model. It's quite straightforward. So here, we just prepare the lock and try to find the connection. So it's quite straightforward. However, it suffers from heavy lock contention if we want to deal with large concurrency connections. And the memory overhead is quite large. So I just show you some number here. And it suffers from the heavy context switch. So let's try to actor model, which as long as the messaging passage. So if we use an actor model, the code will be more elegant since we can abstract the operation for the memory. However, the problem for such model includes, first thing is copy overhead. So we have to perform every operation by means of expensive memory copy. And we still have to deal with the synchronization, meaning that it's hard to achieve true high performance for concurrency scenario. And in this case, we still suffer from the memory pressure. So how about modify the code base to make everything lag-free like this? So we can try to make the code base with operation which is lag-free almost everywhere. So I think this is possible, but it's heavy modification against the current code base. And we have to think about the problem for typical problem such as ABA. And in this case, this is just an attempt to achieve lag-free, but which doesn't mean wait-free. So it's still possible slower than using lag. So right now, we try to think about a different approach. Our idea is to modify the source code without a heavy change. So unlike KDB, Django and so on. And we want to keep the existing data structure, such as skippy list. And we try to follow the existing control flow as well. So the first idea to achieve higher performance is to separation for I/O and computation. We introduce three kinds of thread: main thread, worker thread, and server thread. And we tweak the read workload. Eventually, we change the write consistency. So I think this is very, very common for such design. However, still very interesting. Let's go through. So initially, we have the TCP connection. So here, we accept the connection, and we can do load balance. Then we try to dispatch the connection to the worker thread. So here, we can have several worker threads which are in charge of the client I/O. So everything in the worker thread is almost write operation. And then we can delegate the write command to server thread. So it deals with almost all the write operation here. So this is the interaction among master, worker, and server thread. The benefit of such design includes we can handle the connection quite straightforward, and still we can do load balancing based on this model, so we can delegate the connection from the master thread to dedicate worker thread, depending on the scenario. In our research prototype, we are using round robin, and then maybe we can change the scenario or introduce some strategy based on the different workload. And I think the best thing for such model is there is no contention meaning that you don't have to copy from from the different entity or to wait for certain signals. And this is just a simplified code listing for the code listing in the master thread. So here is duty. I mean, the duty of master thread is to accept TC connection, and later it will dispute the connection. So in this case, accept connection and dispute. Again, there's no lock contention, and the latency should be under control. So is near deterministic. And it's possible to achieve high throughput since it just pass through the connection to the certain worker thread. And this is NUMA friendly, meaning that it's possible to fit for the complex configuration for modern hardwares. And inside the worker thread, the simplified workflow looks like this. So we don't rely on typical locks. So here we are using RCU read lock provided by the Userspace RCU. And here we modify the existing dictionary design. So in this case, this is lock-free as well. So in this section, there is no traditional lock operation, but still we ensure the consistency for all the read operation. In the meanwhile, we can deal with the memory management in lock-free environment. Eventually, we have the server thread, which is in charge of the write operation. So there is only one writer and multiple reader. Right? I think the code is quite straightforward. I just ignore the details, but many of the routine are using the existing code base. So the reason we think the approach is better, I mean for better scalability, lower latency, is it's possible to get the optimal CPU utilization based on the well-structured design through master, worker, and server consolidation. And for the memory access pattern, we ensure all the workers stay in local, meaning that in your NUMA-aware system, this can achieve much lower latency. And for the cross-NUMA traffic, only for writer should be affected. And another thing is client migration. So meaning that the design is still NUMA friendly. So let's go through the detail for the lock-free design. Take get command, for example. So the get command is implemented in worker thread. So again, we see RCU lock here. So right now, we use our own dictionary implementation, Q dictionary find. So it is lock-free hash lookup. And this one is still lock-free. So by means of Userspace RCU, we can achieve zero synchronization overhead. Later, I will show you the performance evaluation, and I think this is the key difference comparing to the existing high-performance Redis fork. And right now, it's just the distribution for read and write operation. So for read operation, there is 0 cross-thread communication, 0 memory barrier, almost 0. So I should write almost 0 atomic operation, and almost 0 lock acquisitions. So I should refine the speaking deck, so it's almost. And for the write operation, since we ensure there's only one writer, so it is very ideal to adapt the use scenario of Userspace RCU. Okay, so this is my setup. So we are using the recent Intel processor, I mean the consumer grade Intel processor, and this is the setup for the Mentier benchmark. Okay, so inside Userspace RCU, there are many flavors, but recently Userspace RCU only provides 4 flavors, meaning that the signal-based implementation was deprecated almost 2 years ago. So we are going to evaluate the existing RCU flavor along with different scenarios, like 10 to 1, 1,000 to 1, and 1 to 1 read-write ratio. And we measure the throughput and the latency, including tail latency. Okay, so the first scenario is around the cache scenario. So it's used to simulate the typical cache usage, 1,000 to 1. 100 to 1. So if you check the diagram carefully, there are many flavors. So in this case, we evaluate QSBR, BR, memory barrier, MB, and the signal, which is deprecated in recent Userspace RCU. This is get. Set, get. And the latency for the average latency for set, average latency for the get, and 50 percentile for the set latency, 50 percentile for get latency, and 99 percentile, and even 99.9 percentile. Get it? Okay. This one should be interesting since it's very challenging. So 10 to 1. So in 10 to 1 benchmarking, you can see the distribution for different flavor is quite clear. So it's not so small as the previous one. Okay, set, get, average latency for get, 50 percentile for set, and get, 99 percentile latency for set and for get. Right? This one is a tail latency. So again, here. So it doesn't matter to pick up the proper Userspace RCU flavor if you want to achieve lower tail latency. And for the 1-to-1 ratio simulation is is quite similar to 10-to-1. So I will not show the detail, but later I will put the raw evaluation results in the final speaking deck. All right. So right now we are going to compare our research prototype with Valkey, and here this is our setup. Meanwhile, we are thinking about the pipeline, which means it allows sending multiple requests without waiting for individual response. So I think this is crucial for evaluating our implementation and to ensure our research prototype is useful in real-world setup. Okay, so benchmark time. Our research prototype is in the green and the blue line. So this one is quite interesting if we want to change the configuration for Userspace RCU, and we can even change the use scenario. So the user scenario based on Userspace RCU varies a lot because we try to modify the work thread, and we try to modify the strategy for load balancing and some other details. But the result is still, I think, still very interesting that it's possible to outperform Valkey in minimal change, making it suitable for high concurrent environments. So this one is for throughput. This one is for the average latency. So Valkey here is here, and our implementation is showing the steady results for lower latency. And how about the 50 percentile? For 50 percentile, it's quite interesting that by means of Userspace RCU, it's still possible to have higher latency if we do not select the flavor carefully. So we're still trying to figure out the reason. Maybe we have to collaborate with Userspace RCU hackers. And for the tail latency, so here, 99 percentile. I think this is the most interesting part. So Valkey itself is quite stable for tail latency. However, in our setup, the distribution is, is quite different. So, as I mentioned earlier, we are still trying to understand the reason why the distribution is hard to predict or hard to recognize. Still, I'm showing this diagram for the configuration for Userspace RCU setup, along with different flavor, work thread amounts, and the way you perform load balancing and so on. So if we want real low tail latency, we do need the strategy to tweak based on the workload. Right. So here, this one is interesting. Maybe we have to prepare the setup for other computer, especially for the for the real server grade systems. Okay, this is our observation. So we have the 8-thread and the 6-thread different kind of configuration, and for the most most use case, our research prototype is outperforming Valkey's. For the recent development of Valkey's code base. For the latency matrix, I think this one is quite interesting. So in several cases, our research prototype can have much lower latency. However, for the tail latency, it's not stable. Maybe it was resulting from the internal state of Userspace RCU. And we try to use different versions of Userspace RCU library, and we get the different results. So we still feel frustrated for this one. We try use the version last year and the recent Git head, and we get different illustration for the benchmarking. Meaning that we have to recognize the detail in order to make the tail latency slow and stable. Finally, I want to emphasize the reason why RCU's idea for Valkey. In our setup, from the observation, we can see is optimized for the read operation, meaning that there's no synchronization overhead. And the latency right now is deterministic, meaning that we don't suffer from blocking, waiting, contention. And for the integration of Userspace RCU, we can achieve cache-friendly design. In the meanwhile, the memory safety is guaranteed by means of Userspace RCU, so we can perform memory reclamation automatically. And this system should be more scalable compared to Valkey. I think you already know this advantage. So RCU itself is really powerful, and we should utilize the existing data structure provided by Userspace RCU. In fact, in our implementation, we just provide thin wrapper for the data structure provided by Userspace RCU. And as I mentioned earlier, the memory recommunication can be guaranteed, and the hash table right now can group or think automatically. So this one should be considered if we want to improve the code base of Valkey. So I think the observation is quite interesting that we changed the Valkey. In fact, we changed Redis. Okay, so we changed the Redis in 2,000 lines of code, and we can achieve a visible performance gain and a much lower latency. Okay, so so far we ensure that our research prototype is useful. The reason why it's useful is, first, we try to eliminate lock contention through RCU-based lock-free data structure, and we make the key value store, the get and set operation more scalable, meaning that we care about the read-heavy workload, and then we can use RCU along with our own lock-free data structure to make the key value store work in multi-threaded environment. And still, we ensure the thread safety, memory safety, without heavy code change. So I think this idea for further consideration if Valkey wants to achieve higher performance. So everything here is just just a research prototype, and I wish we can collaborate here. Okay, so do you have any question?
When you compare it to the Valkey, did you use threads, IO threading in Valkey? Yeah.
Yes.
Okay. How many?
In our cell, we can only say eight IO threads.
Eight.
Yeah. So the workload should be diverse, but we have a limited idea for the scenario. So we have to prepare more hardware and prepare the use case. Since we only pick out the numbers, maybe it's suitable for benchmarking purpose, not suitable for the real case.
Have you looked much into the memory overhead that is needed for the lock-free data structures? What we've noticed a lot with some of our, so I work for Amazon and we do Elasticache, a managed caching service. Most of our workloads are bound on the amount of DRAM. They're not bound on throughput. So have you done much investigation optimizing the memory? Like, does it use more memory or?
Yeah. So I think the question is good, but we have no idea how to measure Userspace RCU memory footprint in fair way, right? The memory recommendation is not taken in deterministic way. So we even submit some issue like this, and we didn't get the positive response. So if we want to measure the memory footprint in the robust way, we have to couple with Userspace RCU first, yeah, instead of the bridge code for Valkey. Yeah. So it takes time for our research, but you can try our code base. Yeah. Okay. Thanks for coming.